applications of direct sequence spread spectrum. Let me reopen it once again. Now we'll go with the applications of DSSS. Okay, so the first application is low detectability signal transmission. This is the first application. So what they'll do here is in this low detectability signal transmission, what they'll do is wantedly they will reduce the signal spectral density. It means that the amount of power with respect to the frequency. Okay, so that signal spectral density is kept low. Intentionally they'll make it low. Okay, so that what happens when it is transmitting through the channel. Okay, so if some noise signal is present, okay, noise signal power will be more when compared with the signal that is transmitted. So it means that the received signal PR by PN value will be very much less than 1. Okay, so in this case what happens? The signal that is transmitted will not be the person will not be able to receive this particular signal because of its low strength. Okay, if he has to retrieve back the original signal, then what he has to do? He has to use the same PN sequence, whatever PN sequence it is used at the transmitter end, the same PN sequence should also be used at the receiver end. So this is the first application. The second application is code division, multiple access. So this is one more important multiplexing techniques. So code division multiplexing. So here what happens? I'll have a single channel and I'll have different transmitters and I'll have the different receivers. Okay, so what will happen? The transmitter has to send the information through the same channel. Okay, so what it will do here, different transmitters will use a different PN sequence. Okay, so even if since they are using different different PN sequence, different transmitters uses different PN sequence. Even if it is transmitted through the channel, okay, so the receivers, all the receivers may get the information, but all the receivers will not be able to decode it. The reason behind that is, see, since we are using direct sequence spectrum here, what will happen? The transmitter signal will be spreaded by using the PN sequence. So only if this information is available at the receiver, that will be able to get back the original signal. So here what happens? This PN sequence, whatever is transmitted, it will use a different PN sequence. So the receiver with that PN sequence will only be able to get back the original signal. So since different PN sequences are used here, even though you are transmitting the information through the same channel, the received signal can be obtained easily. So that is what the CDMA technique. Okay, then comes wireless LAN. Okay, local area network. So here, see, this is mainly employed in IEEE 80.11 standard. Okay, this is used in mobile phones. Okay, so what will happen here is since we are using different PN sequence, it will this discrete direct sequence spectrum, what it will do, it will prevent if anybody want to listen to the data which is said to be the EVAS wrapping. Okay, EVAS wrapping. So if I'm transmitting it through the open space, if somebody want to listen to that data, okay, so this DSSS will avoid that EVAS wrapping. Okay, and one more thing is it will also help to avoid hacking. Okay, so that's why this wireless LANs are used in wireless LANs. Even this direct sequence spectrum is used. The next application is The next application is GNSS. GNSS is nothing but Global Navigation Satellite System. Okay, here what will happen? See this the DSS, again this DSS is used so that the signal gain, so that what happens here, since this is the satellite communication, here what happens, it uses DSSS, as this gives a signal gain by spreading the signal out over a wide bandwidth. Okay, it means that the DSSS is used. Okay, so what is the use of this DSSS? Okay, it will spread the bandwidth. Okay, the spreading of bandwidth will happen. Okay, since the spreading of bandwidth is happening, the same signal can be transmitted through the different signals can be transmitted through the same channel. Okay, so let me consider I have different satellites. Okay, and each satellite will use this DSSS. Okay, and what happens, because of the spreading of the signal that is transmitted, even though you are transmitting it through the channel, the mutual interference will not happen. That is what your fourth application. And coming to the fifth application, communication over channel with multipath. So here what happens is, again here it is mainly used in the mobile communication. So mobile communication, it will having multipath propagation. What do you mean by multipath propagation? Multipath propagation in the sense, the same signal will reach the receiver in different paths. Okay, so because of which the time dispersion will happen. But what is happening here, we are using the direct sequence spread spectrum here, which is what it is doing, it is spreading the signal bandwidth. The signal bandwidth is spreaded. Okay, since the signal bandwidth is spreaded, okay, so the received signal, whatever signal we are receiving at the receiver, okay, after despreading, this effect of multipath will be eliminated. Okay, so these are some of the applications which are using direct sequence spread spectrum. Okay. Now, I hope this is clear to you. These are some of the applications. See, everywhere the advantage of using this DSSS is highlighted. Okay, so now we'll go with the next spread spectrum. So here, if you just observe what is happening, see, I'll just show you the waveform. There is some disadvantage with this method. Okay, let me just highlight that disadvantage here. So this is a this is 1 bit duration. TB is 1 bit duration. In each bit duration, we are transmitting the PN sequence. Okay, so if you want to obtain the output properly, the received signal should not contain any interference signal or the jamming signal. What we need to do, we need to increase N value. But what happens practically if you increase the N value? See, here I've just shown you the sharp cutoff. Okay, sharply it is changing from here it is -1, suddenly it is changing to 1. Okay, so this here I have the discontinuity. Discontinuities will not happen suddenly. So for that, what you'll have, you will have the rise time, and it will be constant for some time, and then it will have the fall time. Okay, so rise time, fall time, everything it should be accommodated in the TB sequence. So what happens? The more the N value, the bandwidth required will be more. Okay, so which is again disadvantageous, and because of this rise time and fall time, still the bandwidth is more. Okay, so that is what the disadvantage with the direct sequence spread spectrum. Okay, so to overcome this, we are going with the frequency hop spread spectrum. Okay, so as the name implies, okay, here the frequency of the spread spectrum. Okay, here what we are doing, we will be using different frequencies and will modulate the signal. Okay, so here we have just used only one carrier and we have spreaded it. But when it comes to the frequency of spread spectrum, it uses different carrier signals. Okay, so since it is using different carrier signals, you can either go with BFSK, generally MFSK. MFSK in the sense, M can be any value like 2, 4, 8, 16, 32, like this, it can take any value. But if it is binary, binary means M will be equal to 2. Okay, so we have already seen how the BFSK will be transmitted, or like what is the modulation and what is the demodulation of the message signal using the frequency shift keying, that we have already seen. Okay, so what was happening in BFSK? So if this is what 0, 1, 0, something like this I have. So this is my data. Okay, 0 will be represented 0, 1, 0. Okay, so what we'll have? We'll have two carriers. Carriers phi 1 and phi 2 are the two carriers. Okay, so let me just take the carrier waveform. I'm just taking the carrier waveform here. Okay, so this is a carrier with high frequency, and next I'll take another with low frequency. So what frequency signal will be transmitted? This is what the low frequency signal will be transmitted. When I have one, the high frequency signal will be transmitted. Okay, again 0, the low frequency signal will be transmitted. So here if you just observe, if it is BFSK, it is hopping between two frequencies. So if it is 0, it will hop, it will take the signal with low frequency. If it is 1, it will take the signal with high frequency. Okay, so this is what is happening in the BFSK. Okay, in general, MFSK means like MFSK means M value can take either 4, 8, 16, like that so on. Okay, so here in BFSK we have B cos 2 pi f1t. This is what the equation if I have symbol. Or it can be equal to root 2 EB by TB cos 2 pi F2T if I have symbol 0. So this is what the carriers we have used in the BFSK. Similarly, in the MFSK, M value can take 4, 8, 16. This 4 indicates number of carriers that is required. Okay, number of carriers that is required. So I need 4 carriers, in this sense 4 signals. Okay, so how many bits this 4 carriers will take? Number of bits will be equal to, okay, because M is equal to 4, we have already seen M is equal to 4, it is 2 power k. Okay, so 2 power k is nothing but 2 square. So k value is equal to 2. So number of bits to represent MFSK is 2 bits. Okay, so 2 bits will group together 0, 0, 0, 1, 1, 0, 1, 1. This like this it will group together. So I have 4 different combinations. So I need 4 frequencies like F0, F1, F2, F3. So I need to use 4 carriers here. Okay, the disadvantage with this is the more the number of the more the M value, the more the number of carriers you have to use. So in the if you take the coherent detection, how many carriers you are using at the transmitter end, the same number of carriers should be used at the receiver end. Okay, so the disadvantage is the hardware implementation is little complicated and it's costly also, because in the BFSK we were just generating 2 carrier signal. When it comes to 4 FSK, you need 4 carriers. 8 FSK, you need 8 carriers. Like that it goes. Okay. However, this this technique is mostly used in frequency hop spread spectrum. Okay, so because to overcome the disadvantage what we have the direct sequence spread spectrum, go with the frequency of in the frequency of spectrum, it will use okay, it will use MFSK. And generally, in general, the MFSK signal is noted as A can like root 2 E by the amplitude given as Fi is equal to Fc plus 2I minus 1 minus M into Ft. This is what the generalized equation to calculate this Fi, okay, frequency of the carrier. Okay, so that is given by Fc plus 2I minus 1 minus F plus into Ft. Okay, so what is Fc? Fc is nothing but the center frequency, the center frequency of the transmitted bit. Okay, so I'll just explain you with one example. Let me consider that my M is equal to 4. Okay, example I'm taking, M is equal to 4. It goes. So let me so if I want to calculate F1, F2, okay, and deviation between F1, F2, all that I need, right? So FD is given by 25 kilohertz. Okay, if M is equal to 4, FC is equal to 250 kilohertz, FD is equal to 25 kilohertz. How will you calculate Fi? Fi is nothing but when I is equal to 1. Okay, when I is equal to 1. Okay, generalized equation of Fi will be now equal to Fi is equal to Fc, which is nothing but 250k 10 power 3 plus 2I minus 1 minus M is 4, FD is 25 into 10 power 3. So just rearrange it, Fi will be equal to 250 into 10 power 3 plus 2I minus 5 into 25 into 10 power 3. This is what your Fi. Okay, so what your Fi. Okay, so now I need what should be the frequency F1, F2, F3, F4, because here my M value is 4. I need 4 carrier frequencies. So let me consider I is equal to 1. So here F1 will be equal to 250 into 10 power 3 plus 2I value is 1 minus 5 into 25 into 10 cube. Okay, so if you just simplify, you will get F1 value as 175 kilohertz. So this is what the first carrier frequency. In the same way, when I is equal to 2, if you find F2 will be equal to 225 kilohertz. Same way, you just substitute I is equal to 1, 2, 3 like that. F3, it will be equal to 275 kilohertz. Use the same equation. Using the same equation, you will be able to find this. And I is equal to 3. F4 is I is equal to here it is 3. Here it is 4. I is equal to 4. F4 will be equal to 325 kilohertz. Okay. So since M value is equal to 2, I need to assign this carrier frequencies to the die bits. Why I am calling it as die bits? Because when M is equal to 4, the number of bits required to represent each symbol is 2 bits. So K is equal to 2. Okay, so die bits 0, 0, 0, 1, 1, 0, 1, 1. Okay, so I need to mention what is the transmitted carrier. So if it is 0, 0, I'll assign it to 175 kilohertz. If it is 0, 1, I'll assign it to 225 kilohertz. If it is F3, I will assign that 1, 0, I will assign it to 275 kilohertz. Okay, if it is F4, I'll assign it to 325 kilohertz. Okay, so let me consider I have like 0, 1, 0, 1, 0, 1, 1, 0. Take 0, 0. Here I'll take 1, 1. Okay, so this is what the combination I have. So first what I need to do, I need to split it to die bits. So 0, 1, it should be transmitted by using the carrier with 250 kilohertz. If it is 00, I need to transmit it by using 175 kilohertz. If it is 11, I need to transmit it using 325 kilohertz. If it is 10, I need to transmit it through by using 275 kilohertz. Okay, so this is how the die bits, how the MFSK transmitter will work. Okay, what it will do, it will choose based on the die bits, it will choose one of the carrier frequency and this will be transmitted to the receiver. At the receiver, the demodulation will be done. Demodulation. So if I have, if I receive 225 kilohertz signal, then I need to make it to 01. If I receive 175 kilohertz signal, I need to map it to 00. If I receive 325 kilohertz signal, then I need to map it to 11. Okay, if I receive 275 kilohertz signal, then I have to map it to 10. This is how the normal receiver will work. Okay, so what will happen? The transmitter will transmit these signals. And receiver, what it has to do? It has to do the reverse operation, in the sense, for this frequency, this die bit should be obtained. For this frequency, this die bit should be obtained. For this frequency, this die bit should be obtained. For this frequency, this die bit should be obtained at the receiver end. Okay, so that is how the MFSK transmitter and receiver will work. But here I have just explained you MFSK transmitter and receiver only to give you the awareness like how exactly it is working. Okay, so now the main reason why I have explained you MFSK is that this is useful in frequency hop spread spectrum. Okay, frequency hop spread spectrum. Whenever I say the word spread spectrum, it means spread spectrum. It means that I'm using PN sequence. I'll definitely use PN sequence. See, whatever MSK transfer where I have explained you here, it is without spreading the sequence. Now what we have in our syllabus, we have to go with frequency hop spread spectrum, and this frequency hop spread spectrum, it will use PN sequence. Okay, PN sequence for spreading the signal. Okay, so how exactly it's happening, now we will see. Okay, so first we'll see the FHS transmitter. Okay, FHS. See, in the exam they may ask you, explain the generation and detection of frequency of spread spectrum. Okay, that's how they may give. Or this we will also call as MFSK with the spread spectrum. See, now whatever I'm doing, it is with spread spectrum. Okay, so the block diagram is given in this way. So first I will have the binary data. So the first step here is, first I need to modulate it. So MFSK, I'll use M in the sense MRE FSK modulator. Okay, so what it will do, it has to if I have 0 0 1 1 0 1 0 0 1 0 1 something like this random data, what it has to do, first it has to split to 2 bits, and after splitting it to 2 bits, then it has to modulate it. Okay, so then after modulation, what it do, I will give it to the mixer. Okay, so this entire thing is said to be the mixer. The mixer consists of the multiplier and the band pass filter. Okay, so here what we'll do, and here to this multiplier I have to get another signal. Okay, here the output here will be nothing but the different carriers with different frequency. Let me name that as FJ. Okay, FJ. J can be either F1, F2, F3, F4, like this. Anything it can be. Okay. Now what I need to do, I need to see, I have modulated the signal. After modulation, what I need to do, I need to spread the signal. To spread the signal, what I need PN sequence generator. Okay, so first I have PN sequence generator. PN sequence generator. From the PN sequence generator, I'll recall linear feedback shift register. I've got some PN sequence which was periodic. Okay, which was periodic. So that data I'm getting here. So that will be given to the frequency synthesizer. So what this frequency synthesizer will do is, whatever incoming PN sequence it is getting, okay, so let me consider I'm getting the PN sequence as 0 0 0 1 1 0 1 0 0 1 1, something like this. Okay, so this is what my PN sequence, and it is a periodic sequence. Okay, so let me consider this is what my signal right now. So what I need to do, I need to divide this into some particular bits. Okay, maybe 3 bits, 3 bits, 3 3. Since it is periodic, if I'm not able to get the, I'll show you with example, don't worry. So what will happen, okay, let me take the same sequence which we have got in our previous discussion. Let me take the same thing and I'll explain you because it will become clear for you. Okay, so what was that sequence we have got in our previous class, the PN sequence. PN sequence we have got as 0 0 0 1 0 0 1 1 0 0 1 1 1 1. Again after this, again whatever data I have got here, it will repeat 0 0 0 1 0 0 1 1 0 1 0 1 1 1 1, like that it will repeat. Okay, that's how it goes. Okay, so this is the PN sequence. So what I need to do here, I am getting the PN sequence. Okay, so this PN sequence, this is nothing but the PN sequence. This PN sequence I have to divide into some particular bits, maybe 3 bits or 4 bits or 5 bits, like that. Let me assume that I am dividing it into 3 bits, 3 bits, 3 bits, 3 bits, again 3 bits, 3 bits, 3 bits, 3 bits, like that you need to divide it into 3 bits. Okay, now what we need to do is each bit, each segment, we call it a segment. Each segment should be assigned with some frequency. Okay, assigned with some frequency. See here, since I'm dividing it with 3 bits, so 0 0 0, let me name it as FC0, 0 0 1, FC1, 0 0 1 0, FC2, 0 1 1, FC3, 1 0 0, FC4, 1 0 1, FC5, 1 1 0, FC6, 1 1 1, FC7. Okay, so what will happen here is this PN sequence, it will be segmented like this, and that segmented sequence will be given to the frequency synthesizer, and this frequency synthesizer will allocate the frequencies in this way. If it is 0 0 0, it will allocate FC0. If it is 0 0 1, it will allocate FC1. If it is 0 1 0, it will allocate FC2. Like this allocation will be done by the frequency synthesizer. So let me assume that here whatever I am getting, I'll just denote with FCJ. FCJ. Okay, from the PN sequence. PN sequence is given to the frequency synthesizer, and the output of the frequency synthesizer is given to the mixer, multiplier. So here you will have some cos 2j, here cos 2fj, something like this you will have. So what it means here is, what it means here is, see, you know that cos A, cos B can be represented as cos A minus B, cos A plus B, something like that. What it will provide, this mixer, it will provide you two frequencies, Fj plus Fcj, and another frequency is Fj minus Fcj. Okay, so these are the two frequencies that will come out of this multiplier. Okay, see here I'm saying that it is Fj is the frequency that is coming out of this MFSK. Okay, so it is nothing but, see here I have denoted, right, it is nothing but cos, now cos 2 pi f1t. Okay, so that will be the input to the product modulator here. So since it is f1 is the frequency, I have just denoted it as Fj here. In the same way, here also frequency synthesizer, it will provide you cos 2 Fcj, something like that. Okay, so what happens, it is given to the multiplier. So cos A, cos B, if you apply, you will get as A plus B and A minus B as the frequency components. So the output of this product modulator will be Fj plus Fcj and Fj minus Fcj. Okay, so here what we are doing is we are giving this output signal from the product modulator to band pass filter, and here this band pass filter should be tuned in such a way that it will provide me only the output frequency Fj plus Fcj. only this component will come out of this band pass filter. Only the frequency components which is ranging in this, only that component should come out, and whatever component with respect to Fj minus Fcj, that should not be allowed to pass through the band pass filter. So this is said to be the mixer. This entire combination of product modulator and the band pass filter is said to be the mixer. Okay, and this here what we are doing, we are converting Fj to Fj plus Fcj. So that is the reason it is said to be up conversion mixer. Up conversion mixer. Okay, so this is so whatever output I am getting here, whatever output I am getting here, that is nothing but the Fs signal, Fh, frequency of spread spectrum signal. Okay, frequency of spread spectrum signal. So using this PN sequence, again here also we are increasing the bandwidth. So this is all related to the transmitter. Okay, hope you understood the transmitter. Yes. Hope the transmitter is clear. Is it clear, ma'am?
Yes, ma'am.
Okay. Now I'll go with the receiver. Okay, let me just brief you once again. Transmitter, what it is doing. First, I have the binary data. Okay, if it is m is equal to 4 specifically, the incoming data should be divided into 2 bits. Okay, so and that is given to the MFSK modulator. So each 2 bits will be assigned with some frequency, and that will be the output of this modulator. Let me name that frequency as Fj. Okay, and here what I need to do, I need to use the spread spectrum techniques as well. So what I'm doing, I need PN sequence to spread the spectrum. So here I'm generating the PN sequence that is given to the frequency synthesizer. Okay, the reason why this is given to the this frequency synthesizer is like here we need to here we are getting different frequency signals, f1, f2, f3, f4, like that we are getting different frequency signals that should be spreaded. Okay, that signal should be spreaded. To spread that, we are using this PN sequence. So the output of this PN sequence is given to the frequency synthesizer. So how this PN sequence is given to this frequency synthesizer is, so whatever PN sequence I am getting, that should be segmented first. Okay, it can be segmented to either 2 bits, 3 bits, 4 bits, 5 bits, like that. Okay, and when you segment it, you need to assign a particular frequency to this particular segment. Okay, so that frequency allocation of the segmented PN sequence is done in frequency synthesizer. That so the output of that I'm just taking it as FCJ. FCJ is nothing but the frequency of the segmented PN sequence, and that is given to the modulator. Okay, product mixer. This entire thing is said to be the mixer, and the mixer consists of multiplier and band pass filter. So what this multiplier will do, it will take Fj and Fcj and it will provide you 2 output signals. It can be Fj plus Fcj, and the other one is Fj minus Fcj. Okay, so that those two the signals with this frequencies will be the output. Okay, so now what I need, I don't need both of them to come out. So what, that is the reason I'm using the band pass filter. Okay, so here the band pass filter should be tuned in such a way that it will provide me only the some output. Okay, some output in this is Fj plus Fcj. Okay, and what should happen to Fj minus Fcj? It should attenuate it. Okay, Fj minus Fcj should be attenuated, and I should get the output as only Fj plus Fcj. Okay, so that is the output here. So whatever signal I'm getting here, I'm calling it as FHSS signal. Okay, and this should be transmitted now. Okay, so now again I have to take the FHSS receiver. Okay, receiver. So my receiver should be in this way. It should receive the signal. It should receive the signal. Receive signal. Okay, then this received signal should be again given to the mixer. Okay, mixer. mixer as transmitter end, the same PN sequence should be generated with the receiver end as well. Okay, so here again I'll have the PN sequence generator, PN sequence generator, PN sequence generator that should be given to the synthesizer, frequency synthesizer, frequency synthesizer. So if the transmitter in if we have segmented to 3 bits, here also it should be segmented to 3 bits. Okay, and whatever frequencies were allocated in the transmitter in, the same frequencies should be allocated at the receiver end as well. Okay, so here my incoming data is nothing but Fj plus Fcj. Okay, Fj plus Fcj is the received signal because the transmitter is emitting only this frequency signal, and from this frequency synthesizer I'll get the Fcj. Again Fcj will be obtained. Okay, so this product modulator, it will provide you two outputs. One is Fj plus Fcj plus Fcj, and this is the first signal that will be out of this multiplier, and the second one is Fj plus Fcj minus Fcj. Okay, so what I should do now, I have to use a band pass filter in such a way that it will take only the difference term. So this is the difference term. So the band pass filter should be tuned in such a way that it will take the difference term, and so that my output will be nothing but Fj plus Fcj minus Fcj. Okay, so this minus Fcj and plus Fcj will get cancelled. So I'll have Fj. Okay, so if you just observe here, the output of the modulator is Fj. Now what I need to do, I need to demodulate this so that I'll get the actual binary data. So I'll give this to the MFSK demodulator, or we call it as detector also, detector. Okay, so that from the Fj, whatever Fj it is getting, from that it will give you the estimated binary data. Estimated binary data. This will be the output of your FHF frequency of spectrum receiver. Okay, so this is the overall process. So let me just put this entire thing in one block diagram. Okay, so the complete block diagram of FHSS transmitter and receiver. Okay, so let me just draw the diagram. First I'll have the incoming data or information signal that is given to the encoder. Okay, from the encoder it is given to the FSK modulator, MFSK or FSK modulator. And that should be the mixer. So the mixer will be giving the input from the frequency synthesizer. So how frequency synthesizer. Okay, then the output of the mixer. This entire thing is nothing but the transmitter part now. This entire nothing but the transmitter part. Okay, that should channel. Then the output of the channel should be given to the mixer again. Okay, mixer. Okay, mixer. To the mixer, one input is the received signal, and the other input is from frequency synthesizer. Whatever we are using here, the same thing should be used here also. Synthesis. Okay, here it is PN sequence. From the PN sequence. Then what I need to do? I need to demodulate it. So from here, I'll give it to the FSK demodulator. Here, from that, I'll give it to the decoder. Finally, Encoding means like you may add some redundancy. Okay, so by adding the redundancy, we'll be able to remove the errors. So since here we are adding the redundancy, here we need to remove at the receiver end. You need to remove the redundancy. So decoder, and finally the output, whatever output you are getting is nothing but the estimated data sequence. Estimated data sequence. Estimated data sequence. So this is a complete block diagram of your FHSS transmitter and receiver. Okay, so how exactly the frequency is hopping, that I'll explain you in the next topic, which is nothing but FHSS. FHSS, as I mentioned, it is nothing but frequency of spread spectrum. So this frequency of spread spectrum, it is divided into two types. One is slow FHSS and the other one is fast FHSS. Okay, so these are the two types. So first we will go with the slow FHSS. Okay, before going to the explanation of this slow FHSS, let me introduce some different notations. Like, so first I will take as TB. TB is nothing but the bit duration. If I know TB, I'll be able to find RB. RB is nothing but the bit rate. Okay, RB is nothing but 1 by TB, right? So RB is nothing but bit rate. Next, TS, symbol rate, symbol duration. So if you just observe in the transmitter what we are doing, the incoming data is divided into two bits if it is m is equal to 4. Okay, so here we are taking two bits together. So this complete thing is nothing but symbol. So you all are aware of all this. Anyway, I'm just giving you some hint to recall. Okay, symbol duration. So RS is nothing but symbol rate. Next, TC or TH. TC is said to be the chip duration, or it is also said to be hop duration. Okay, here TC. See, if you just recall here what we are doing, we are segmenting 3 bits together. We are segmenting 3 bits together. Okay, since we are segmenting 3 bits together, this complete duration. So all, let me take this 110. So 11110. Okay, so this complete thing is said to be TC. Okay, hop duration or chip duration. In the normal direct sequence spread spectrum, what we did, each bit we have taken as one chip duration. This entire thing is nothing but one chip duration. Okay, one chip duration. But in the frequency of spread spectrum, we will combine 3 bits or 4 bits. How many bits it's left to you? So all that will be, all that together is said to be. Let me name this as k bits. All these k bits together will provide you the chip duration. Okay, so EC is nothing but the chip duration or hop duration. Okay, so RC or RH is said to be the chip hop rate. Hopping. Okay, first you need to know what is hopping. Hopping means jumping from one frequency to the other frequency. That is said to be hopping. Okay, so this is said to be the hop rate or chip rate. Okay, so before going in detail explanation about this, what's the time now? 11:58. Class is until 11:55. So whose class is there in the next chart? Whose class is there in the next chart? Anybody?
Microwaves and antenna.
Okay. Okay, fine. So I will just wind up my class here. Tomorrow's class, I'll quickly teach you slow frequency of spread spectrum and fast frequency of spread spectrum. How exactly it is working, that we'll see in the tomorrow's class. Because if I start that now, like I need some time to explain. So that's why let me not start now. I'll start it tomorrow only. Okay. So this how this frequency of spread spectrum transmitter and receiver is working is clear to you, right? Is the transmitter and receiver clear to you? How the transmitter is able to transmit the signal and how the receiver is able to demodulate the signal. Is it clear?
Yes, ma'am. Yes, ma'am.
Okay, okay, okay. Fine. Tomorrow I'll do the the class is done for the day. If you have any doubts, you can ask me. Otherwise, you can leave the class. Thank you.
Thank you, ma'am.
Thank you. Thank you.